Hey everyone, welcome back to WirelessPro. Today, we're diving into one of the most critical and complex challenges in wireless communication, channel estimation. With 5G pushing the limits and 6G on the horizon, we need smarter, faster, and more adaptive ways to understand how signals travel through the air. That's where artificial intelligence and machine learning come in. In this video, we'll explore how AI is transforming channel estimation from a rigid mathematical process into a dynamic, learning-driven system. To motivate this paradigm shift, let's take a look at a real-world challenge modern researchers are currently tackling. Imagine a drone flying through a dense urban environment. It isn't just sending data, it's sensing its surroundings, avoiding obstacles, and adapting to rapidly changing conditions. This is Integrated Sensing and Communication, or ISAC, a cutting-edge scenario with a ton of moving parts. Here's the challenge. With drones moving at high speeds, significant Doppler shifts are introduced, and the presence of buildings and obstacles make for complex multipath signal propagation. These, compounded with limited available pilot signals, cause traditional channel estimation methods to struggle, and we'll soon find out why. But that's just the tip of the iceberg when it comes to the complexity involved in ISAC. Ultimately, the drones need to understand their channel in real time, with precision and with limited resources. Take a look at the visualizations from Keysight's 6GFR3 emulation setup. These graphs highlight how unpredictable and dynamic the wireless environment becomes when communication and sensing are tightly coupled. It's a perfect storm of complexity, and AI is the tool we need to navigate it. But let's rewind for a second. How does channel estimation actually work? It starts with pilots, known reference signals like DMRS, SRS, CSIRS, PTRS, and PRS. These are sprinkled across the transmission to help the receiver figure out how the signal was changed by the environment. In OFDM, we transmit data across multiple subcarriers over time, which forms a time-frequency grid, kind of like a spreadsheet of signal snapshots. Pilots are placed in specific cells, and the receiver uses them to estimate the channel's behavior across the grid. However, in complex environments, the channel becomes highly dynamic and nonlinear, making pilot-based traditional estimates increasingly difficult to apply. Traditional estimators like least squares, or LS, LMMSE, and MMSE are like basic autopilots. LS is simple but ignores noise. LMMSE tries to balance complexity and performance, but relies on partial channel knowledge and makes channel assumptions, while MMSE is optimal but computationally demanding. In real-world scenarios, these methods start to break down. That's why researchers have explored advanced techniques. Interpolation smooths out missing data between pilot positions, iterative refinement improves estimates step by step, and compressed sensing reconstructs sparse signals using fewer measurements. These methods help, but they still rely on assumptions and handcrafted logic. To truly adapt to complexity, we need a learning-based approach. That's where AI and ML begin to reshape the problem. To make channel estimation an AI problem, we start by abstracting the channel's key features: temporal dependencies, spatial complexity, frequency selectivity, and sparsity. These are just some example patterns that neural networks can learn. Instead of solving equations, we can train models to recognize these patterns. CNNs and transformers are great for spatial features. RNNs and LSTMs handle time-based changes, and autoencoders compress and reconstruct complex signals. It's quite like giving our receivers a brain that learns from experience and adapts to new environments. Now it's time to design this AI brain. Should we use a lightweight CNN for fast inference, a deep transformer for complex environments, or a hybrid model that balances both? We consider latency, compute power, data availability, and performance needs. But it doesn't stop at choosing a model architecture. We also tune hyperparameters like the number of layers and choose specific activation layers. These fine-grained decisions help us optimize the model for specific deployment targets. Training these AI models requires massive amounts of data, but collecting real-world wireless data is expensive, time-consuming, and often impractical, especially for edge cases. That's why we simulate. Using 3 GPP standardized channel models, we generate synthetic datasets that span a wide range of conditions: urban, rural, high-speed mobility, low SNR, different antenna configurations, and fading profiles. Simulation gives us control, repeatability, and diversity. It ensures our models can generalize, performing well even in environments they haven't seen before. But generating data and choosing the right architecture is just the beginning. The beauty lies in their integration with the channel estimation pipeline. AI doesn't replace traditional channel estimation, it amplifies it. Think of it as a smart co-pilot that builds on top of the backbone that is traditional estimation methods. The updated channel estimation workflow now looks like this. We start by generating reference signals and channel conditions. Then we apply traditional estimators like LS or MMSE to the pilot signals to get baseline estimates, which act as input to the AI model, and are paired with the true channel responses, which act as labeled data, the foundation of supervised learning. Once trained, the model performs inference, estimating the full channel and assessing its accuracy. It's a modular, scalable pipeline that fits seamlessly into existing physical layer processing. Let's take a peek under the hood. This is our WirelessPro platform, where we build and test AI models for channel estimation. In our Python-based environment, you'll find project files for data generation, model training, and inference. The architecture we're using here is a CNN-based model, optimized for spatial channel learning. Once trained, the model is exported in formats like ONNX for hardware-agnostic deployment across platforms. Multi-core parallelism and batch inference also assist in meeting real-time constraints, and our simulation pipeline is aligned with 3 GPP-compliant configurations, including antenna setups, channel models, and SNR profiles. To validate readiness, we track performance using NMSE for estimation accuracy and throughput for real-time responsiveness. These metrics help us fine-tune the model and ensure it's ready for real-world deployment. As we look ahead, AI and ML offer something traditional methods can't: adaptability in complex and dynamic wireless environments. But that doesn't mean we throw out the old playbook. Traditional methods remain valuable as baselines and fallbacks until we can interpret and trust the results of AI/ML enough for it to stand alone. In the meantime, WirelessPro enables rapid prototyping and experimentation, helping us move towards that future where wireless communication won't rely on dense pilot signals, which add overhead, accurate channel models, which are hard to obtain, prior knowledge of noise statistics, and explicit assumptions about mobility, fading, or antenna configuration. This is the vision: intelligent, flexible, and efficient wireless systems powered by AI supercharged channel estimation. Thanks for watching, and we'll see you in the next one.